Hey everyone, so in this lecture we will study about linked list, only the basics of the linked list, in which we study the singly linked list. Okay, so let's get started. Alright, so starting with the definition, what exactly a linked list is? So it is a linear data structure where the nodes are linked together. It is a linear data structure in which the nodes are linked together, and a very popular analogy that you can think of to understand a linked list is, see this example. It is a train in which the first compartment is the engine. It is engine which is connected with, let's call it coach number 1, and then coach number 2. This engine is linked with this coach. This C1, coach 1, is linked with both engine and coach 2. Okay? And what if you stand here, you are in coach 2. You are in coach 2 and you want to go towards the engine. So you can walk over this link and then go to C1 and add C1. You can again walk over to the link to reach engine, but there is no way directly from C2 to go to this engine. This is not possible. Okay, so this is what a linked list is. There are some data objects. I am vaguely explaining. There are certain data objects which are present at different locations in memory. Say location 100, 200, 250, 300, but somehow they are linked in such a way that if you are at location 100, you can go to 200 directly. If you are at 200, you can go to 250. If you are at 250, you can go to 300. But if you are at 100, you can't bypass 200 to go to 250. It's not possible. So certain data objects present somewhere in memory are linked together in such a way that sequentially you can traverse this object in order to get to the last one. So this sort of data structure is called as a linked list, or specifically a singly linked list. But in general, if you are only talking about linked list, by default it is always a singly linked list. There are certain variations in which you can change the link in such a way that the link can be bidirectional, a link can be circular in nature, and so on. We'll discuss the variation later on, but for now this is a singly linked list. Okay, all right. So key analogy: a train coach is linked to an engine. There is a link in between the subsequent coaches and these engines. Okay, now there are certain parameters. So what exactly a node is? Like I told you, a linear data structure where nodes are linked together. So what exactly a node is? Let's see. So each node, every node is a data object that has two parameters. The first is the data. The second is the next pointer or the reference, which is the link. So you can think of a node as a data object. This is a node. Has two compartments or two sections of a node. The first is data, the value of the value that you will be storing in this node. Second is the reference of the next data object or next pointer. Okay, and this is the value and this is pointer to the next node. And I am only talking about the basic linked list data object, which is a singly linked list. Only one link we are storing, only one reference pointer we are storing. Alright. So you can think of as an example. So in this case, you have, let's have another one, value 1. There is another node with value 2 and value 3. That's it. Okay, so there are three nodes. This is node 1 with data as 1 and next pointer pointing towards node 2, node 2 with data as 1 and the value of pointer pointing towards node 3, and node 3 with value as 1, and if you assume that it is the last node of this list, in that case it will always point to null. It will always point to null. So whatever node is present at the end of the list will always point towards null. That's what like will signify us, it will tell us that it is the end and there are no further nodes attached to this linked list. Okay, so this is what the next point says. The last node points to null always, and this is the end of the list. Otherwise, how will you know that there are further some more nodes present or not? Okay, so every time if you are like dealing with these lists, the last node will always point to null. Okay, and one more important thing, there is also a head of this list. In this case, the engine of the train or the first node of that list is always called the head, and this is it is a very important pointer. So this n1, there will be a pointer which will always point towards the first node or the starting node of the linked list, and this is a very important node. Why it is very important? Because this is the only reference, from which you can reach each and every node present in the linked list. If somehow this head is missed, got missed, in that case the entire list get missed. You can't reach to node 1, you can't reach to node 2. Why? Because in order to reach to node 2, you have to reach first node 1. But since you have lost the pointer to the node 1, you can't reach either node 1, either node 2 or node 3. Subsequently, entire list gets lost. So that's why it's very important to implement your logics in such a way that you should not lose the head pointer. And if you have the head pointer, you can directly reach to node 1, then node 2, then node 3, and so on. Why? Because all the nodes are linked sequentially. So if you have the pointer to the first, if you know the address where exactly n1 is, you can reach to all the subsequent nodes present in this list. That's why the head pointer points to the first node, and all the operations that we're gonna be doing on this list, we always ensure that this head is not lost. Okay, all right. So next is linked list operations. So what operations you can perform on these sequential list? Okay, and the operations include either you can search an element in that list, you can insert an element in the list, you can delete an element in the list. Okay, and insertion and deletion have certain variations, like where exactly you want to insert or delete, but search is straightforward. Search says check whether a specific element is present in this list or not. That's it. Okay, so how will be checking it? Consider an example. One, I'm not splitting the nodes in two components. You can assume that a data and a pointer is already present in each and every node. Okay, this is 2, this is 3, this is 4, and null, right? Suppose you have a linked list, you have a list in which head is given to you, 4 nodes are there, and finally the last node is pointing towards null. Okay, it's the end of the list. So now you need to find an element x present in the list or not. There can only be two scenarios, whether x is present or x is not present. Whether x will be there, x will be present, or x won't be present. And let's name these nodes. Let's call it n1, node 2, n3, and n4. And since the property of the list is in such a way that we only have this pointer, head is always given to you. From where the list is starting will always given to you. So if you want to search an element, in the list, you will always start from head, right? Because it is the only pointer which is given to you, and the property of the list is in such a way that you need to search sequentially. If you want to reach to n4, you should be present at n3. Why? Because address of n4 is only stored in n3, address of n3 is only stored in n2, address of n2 is only stored in n1, and we have the address of n1, which is the head. Okay, so the only way to search is to search sequentially from n1. Check whether x is 1 or not. It is 1. If it is 1, just return. If it is not, go to the next one. Check x is 2 or not. If it is yes, return. Else, go to the next node. Check for 3. If it is 3, in that case return true. No, go to the next one. Check for 4. If it is 4, return it. Else, go to the next one. You will repeat this process till when? Till either you get your x or you get a null. In case you get a null, this is the case when x is not present. If you get null, this is the case that x is not present in the list. Why? Because you have already traversed everything. You have searched starting from the head. You have checked each and every value of the nodes present in the list, and you currently reached to the end of the list, which is the null pointer. Alright, in that case x won't be there. In between, if x is there, then you will anyway get it. Why? Because you are checking it sequentially. So this is what the pseudo code is. Search for this key starting from this head. Okay. Alright, so the code, the logic is you will start with the current. Start with current. Head is given to you. Take a pointer with a name current. Current will initially point to 1. Let me draw it again. 1, 2, 3 and 4. And finally it's null. Okay. So this is current. Initially this is current. Why? Because current is equal to head. You are taking another pointer with a name current and initializing it with head. Head is the first address of the first node in the list, n1. Alright. Now there is a while loop. While current is not equal to null, you keep on checking whether current is null or not. In case for the first time, if the list is having some elements, in that case it won't be null, right? It is head. So current is not null, which is true. If it is true, then you will check whether current.data is equal to the key or not. Whether current.data is equal to the key that you are searching in the list or not. What I am doing is, we are doing check for this one. This is what current.data is. If this one is equal to the key, let's suppose I am searching for, let's suppose the key is, I am searching for 3. Tell me whether 3 is present in the list or not. Okay. The first comparison will be whether 1 is equal to 3 or not. It's not. So it is not equal. So this true, return true won't get executed. This line number 5 will get executed. Update current with current.next. Update current with current.next. So update current. So current will no longer point to 1. Current now will point to 2. Current will point to 2. Okay. And then again, if it is not null, then check if the updated data of current is equal to the key or not. If 2 is equal to 3 or not. Answer is no. You again update current with current.next. Now the current will point to 3. While check current not equal to null, every time before entering inside the loop, we will check whether the end of the list we got or not. In this case, we didn't reach the end. So if condition will execute, current.data is the key. Is 3, which is the value of current.data, is equal to the key which I am searching or not? Answer is yes, it is. Just return true. We found the element. We found the element. Or what if key was 5? What if key was 5? We are searching for 5 in a list having 4 nodes, 1, 2, 3 and 4. In that case, you will end up at this while loop where current is not equal to null. Why? Because we are every time updating the current with current.next. We are every time updating the current if we are not finding the current.data equivalent to the key. In this case, after current will point to 4, we'll again update to currents next, and currents next in this case is null. So current will be null if we are searching for a key which is not present in the list. Current will be null if we are searching for a key which is not present in the list. So this while loop will be false at this point, and you will return false. And you will return false if you didn't find the element and you exhausted your search, the element is not present. That's it. Alright. So now, like, if I have to ask you, what is the worst case time complexity of this operation? Worst case time complexity of this search operation. What will be the worst case? The key is not present. If the key is not present, you end up searching everything. You end up searching each and every node in the list. So it is big O of n, worst case time complexity, if the key is not present. Key not present. If the key is not present, this while loop will execute n times. This while loop will execute n times, and you end up searching everything, and then you will return false. Okay. So big O of n. Right? Easy. Let's move on to the next operation. The next operation in the list is insertion. What exactly insertion is? You want to add another node in the list. Okay. So adding a node can be done in either three ways. There are three ways, either based on the complexity of these operations. Either you can add at beginning. What it is? You already have a list. You already have a list and you want to add a node X at beginning. The new list will look like this. The new list will look like this. Okay. You are adding a node at the start, before the head node, before the current head, right? Next is at the end. You already have a list and you want to add another node at the end of the list. This is the new node. This is X. Okay. And third is after a given key. In a list, a key is given to you, and it's sure that the key is already present in the list. You need to add the new node X after that specific key. Let's assume key K. So new list, updated list would be, this is K, then your new node X, and finally the last one, this one. Okay. So these are the different ways in which you can insert an element in the list. Either it can be beginning or end or somewhere in between after a specific key. Okay. So let's see one by one. First is inserting at the start or beginning. What if you want to insert an element at the beginning of the list? So we'll first take in reference and then we'll go through the pseudocode. Okay. So let's assume you have a list 1, 2, 3, that's it. Okay, you have a linked list with 3 nodes and this is the head. This is the head. Okay, and what operation you need to perform? I need to insert X. I need to insert X at the beginning. I need to insert X at the beginning. So my updated linked list should appear like this. Insert, say 4 at start. So my updated list should look like this after this insert operation. 4, then 1, then 2, 3, null, and the new head should point to 4. The new head should point to 4. Why? Because if you are not, after inserting you haven't updated head will still point to this. And if head is pointing towards 1, then there is no way to reach node 4. Why? Because the link is in forward direction. From 1 you can go to 2, from 2 you can go to 3, from 3 it's the end. There is no way to reach to the newly added node that you have added before the previous head. So therefore it is always mandatory to carefully handle these situations, either insertion, deletion, any operation, to carefully handle such a way that after you have done the operation, head should always point to the starting node of the updated linked list. Alright. Okay. So now let's see the pseudocode. So line number 1, what it says, I am defining a new node with value as x. So it will just create a new node. Okay, it is not linked to anything, just create a new node. Okay, it's initialization of a new node. Then what I am doing, new.next is head, and at this point at line number 2, head is pointing towards 1. At this point head is pointing to 1, pointing to, let me call it n1, n2, n3, pointing to n1. What I have done, I have initialized a new head. This will give me a head with value x, right? Why? Because I need to insert a new node with value x, correct? In our example we have taken x as 4. Okay, and what I am doing, I am new.next, there will be a next pointer of this current node. I am updating it to n1 or head. Head is pointing towards n1. So the operation that I did is just pointed towards this head. Just point it towards head. Create a node, point it towards the current head. Right? What it will do, it will link my new node. It will link my new node to the head. Okay, and finally update the head. Head is new. The new head is the node that I have created just now, that we have created just now. This is very important operation, to update the head pointer in such a way that now head is pointing towards the newly created node. Okay, and just return the head. This will be sufficient. Easy. What I have done, I had a link 1, 2, 3 and null. This was my head. I initialized a new node called x at line number 1. Line number 2, x.next is pointing towards my head. Okay, if I haven't updated anything, previous head will be pointing towards the first node of the existing list. I have created a new node and next is pointing towards head, and then I am updating this head. This is new. I am updating the head to new. So this will become my updated head. Head will no longer point towards 1, head will point to my new node, and I will return this head. Right? Okay, easy one. So now if I have to ask you, what is the worst case time complexity? There is no worst or best, it is only one scenario in which you are adding the element at the start of the list. So there is no looping, there is no traversing, nothing. So it will be a constant time operation. We have just created a node and then updated, there are two updates, updated a link and then updated the head, right? So it will be a constant time operation. Insertion at the beginning of a linked list is a constant time operation. Alright, let's see the next one. The next is inserting at the end. Okay, now what if you need to insert an element with value x to the end of the list? Earlier it was at the beginning, now I need to insert it to the end. For instance, you have a list 1, then 2, then 3 and null. Okay, this is the existing list and your head pointer. head is pointing towards 1. This is your n1, this is n2, this is n3. Okay, now you need to insert an element with value x at the end of the list. What you will do? Simply you will create a new node. Line number 1, create a new node with value as x. Okay, you have 1, then you have 2, then you have 3, and it was null previously. Okay, what you will do? You have done line number 1 will create a new node. You create a new node. This is new with value as x. You have created a new node simply. Okay, now the first case, if head is null, return new. What is this case? This is the case when there is only one. If the list is empty, if head is empty, you just add it and you just create a new node, and by default every new node will always point towards null. By default every newly created node will point to null. We'll see when we try to have this initialization or implementation. Point to null. Explicitly, like, we are not mentioning it, but it is new and it is pointing to null. But generally it is ignored. So since it's a default understanding that a new node will always point towards null until unless you are updating, you are like deliberately updating the next pointer of this new node. Okay. So the first scenario, if head is null, what if the list is empty? Head was itself pointing towards a null value. In that case, just return the newly created node that you have added. That's it. After update, there will be only one node. Why? Because earlier head was pointing towards null. But it's a corner condition, can be ignored. Okay. So now what if there are certain elements present in the list? A regular scenario. 3 elements present in the list and you are trying to add the newly created object towards end of the list, which is after 3, after n3. Okay, so now you take a temporary pointer called current, initialize it with head, initialize it with head. This is my current pointer. Why? Because I have initialized it with head. Okay, so current is pointing towards n1. Now what I have to do? I want to add this newly created element towards the end. So first I need to reach to this point. First I need to reach to the end. That's when I can update this link. Rather than pointing towards null, point it towards new, right? But first I need to reach to this node, which is the last node of the list. How can I reach it? By a loop. Sequentially I will keep on updating it until I reach to the end. Let's see. So while current dot next not equal to null, what I'm doing, I'm checking that my current node at the specific node on which I am checking whether current dot next, the next pointer of this node, is null or not. So if initially it won't be null, so I will just update my current to current dot next. Okay, what it will do, whether current dot next, which is in this case current dot next is pointing towards 2, is null or not. Answer is no. Just update the current. Just update the current. This will be my current. Check again. Current dot next is equal to null. This is the next pointer. Okay. So in this case as well, it is not null. Update it current to this. Now at this point, current dot next is in fact equal to null because we have only 3 elements. If the current is pointing towards n3, the next pointer will always be null, right? At this point, this while will halt, and I have reached a node which is the last node of the linked list, where I have to add the new node that I have created. Correct? Then current dot next is new. What it is? Earlier current, the last node was pointing towards null. I have removed this link and enforced it to point towards the new node that I have created. Current dot next is equal to new. Okay, and return head. Why? Because by default new dot next is anyway null, and since we are adding the element towards the end of the list, there is no change in the head. Still after the insertion, head is pointing towards n1. Is that clear? Correct? What I have done, I have initialized a new node. I have checked, you can, like line number 2 and 3 you can ignore, it's a corner scenario in which the head is initially empty. So just return new. What if there are certain elements present? I need to reach to the last node of that list. To do that, I need to have a while loop. So while current.next initialized current with the head, initialized current with the first node of the list, and checked whether the current.next is null or not. It will be null only for the last node, otherwise it will always point towards the immediate next node which is linked to my current. Okay, if it is not null, in that case the next is a valid node. Move on to the next node and do it, and keep on doing it until you reach to the last, which is the scenario in which my next is not pointing towards any node. Now it is pointing towards null. I am now convinced that I have reached the end of the list, and once I have reached the end of the list, what I have done, we will simply update my pointer. Current.next at this point is null. Update that null to my newly created node. That's it. Okay, and then return the head. You have successfully added an element at the end of the list. Now I have to ask you, what is the worst case? There is no worst and best here. What is the time complexity of this operation? N, right? Why? Because for every insertion at the end, it's the heading. I need to insert at the end. You need to reach to the last node. In order to reach to the last node, you have to traverse everything. It's the sequential read, right? So in order to, this while loop will run n times. So insertion at the end is big O of n operation, right? Okay. Now the next one. Inserting after a key. Again, the third variant of insertion, a key is given to me, and it's also given that it is present in the linked list. For instance, you have 1 pointing towards 2, 3, 4 and null. Okay, now I want to insert, and this is my head. I need to insert a node after, let's say, 3. I need to insert a node after 3. Insert X after 3. Correct? This is the operation that I need to perform. I need to insert a new node after 3 such that the updated linked list will look like this. You have 1, then 2, then 3, then the new node X, and 4 null, right? And it can be anything. This X can be inserted after any key present in the linked list. Okay, so let's see. Insert after this key element X. Insert after a key element X. Okay. All right. So here you need to take care that whenever you are trying to insert an element, like in the previous case as well, we have seen that when you try to insert an element at the end, first you need to reach to the last node. Okay. So in every insertion, whenever you are trying to insert anything after a specific key, okay, you need to reach to that node. Why? In this case, you are trying to insert a new node after 3. Okay, so what will be the scenario? First, you have to reach to this node, and then you need to remove this link, and 3.next you need to link to the new node that you have created. Correct? And which has the value X, and then you need to update the next pointer of the new node with this. Is it clear? That's how you can insert. You have removed the current link and updated 3.next to point to the newly added node and enforced the next of the newly added node towards the previous next of n3. Then you have successfully added x to the linked list after 3. Okay, then now the question is, you need to how can you perform this operation without losing these links? Without losing these links, how can you perform it smoothly? Let's see the code. Update the current with the head. First operation, you already have a head. Update take a current and update it to head. Okay, now current is pointing to the first element present in the linked list or the first node of the list. Okay, now there's a loop. While current is not equal to null and current dot data is not equal to key. While current is not null and the value of the current is not key. Why we are doing it? Because every time we are checking, we want to insert x after this key. In this case, the key is 3. The key is 3. We want to insert x after 3. So if I am at a specific node, starting with the head, if I am at a specific node, I want to insert the new node after this node. So I am checking whether the value of this node is equal to the key or not, right? If it is equal to the key, I will simply add the newly added node after my current one, right? If it is not equal to the key, I will check, I will go on to the next node. If it is not equal to the key, I will update my current to next, so that I move to the next element of the linked list. Okay, in this case, current dot data, the value of the current node is not equal to the key, so I will update the current. Now, is current dot data equal to key? 3. Is 2 equal to 3? Answer is no. Again, I will update it. Now at this point, whether the value of the current node is equal to the key or not, the answer is yes, it is. So further we will stop updating the current. This won't execute once I got the current dot data equal to key. We'll stop it. So at this point, whenever I find an element whose value is equal to the key, I will stop updating my current pointer. Now there can be two scenarios. Either you exhaust the list whether current is equal to null. What if you only have 3 elements, or what if you have only 2 elements? In that case, this while loop will stop with this first condition, which is current is not equal to null. In this case, current will equal to null once you update the current to current dot next. Okay, so this is the boundary condition where the key is not present, but you can assume that key is present. So we'll ignore line 4 and 5, but for corner cases we should always have these checks. Okay, so now I am at the situation is I am pointing towards node 3, which is current. Initialize a new node. Let me remove it. Existing 3 is pointing towards 4. 4 is pointing towards null. Now I'm at line number 6. What it will do, it will initialize a new node. With value x. New node, the next pointer is null, right? Now what I am doing, I am updating the next new dot next. What I am doing, I am updating new dot next, the next pointer. I am enforcing new dot next to point towards current dot next. I am enforcing new dot next is equal to current dot next, and then updating current dot next to new. What I have done, first I have linked my new node with the next element present after current. Then I have removed this link and point current to new. This is important. You can't swap line number 7 and 8. which is the other scenario can be current dot next to new. Other way around I can also write, right? Current dot next is equal to new, and new dot next is current dot next. The answer is no, I can't write this. Why? First operation I need to do is update the next pointer of the new node towards current dot next. Why? Because if before updating my next pointer of the newly created node towards the next one of the current one, if I have somehow removed this node, in that case there is no way to reach to this node. Let me explain. I am at 3. 3 is pointing towards 4, and then there is a node new. If line number 8 you have executed before line number 7, which is this case, current dot next, this is my current. If current dot next is equal to new, if current dot next, what I am doing, I am breaking this, I am updating this link. Initially 3 was pointing towards 4, so I am breaking this link and pointing it towards new. I have broken this link and I have pointed towards new. This is absolutely fine, we need to do this. But you can't do it before. Why? Because now at this point, this 4 is lost. This is lost. There is no way to reach to this current dot previous next, because now current dot next is pointing towards new. This 4 is lost. If you update the next pointer before, in that case it is lost. So that's why in insertion always update the next of the newly created node first and then break this link. Otherwise the chain is broken and there is no way you can reach to this node 4. Why? Because the only way to reach 4 was from 3, which was current dot next was like taking you towards the next node, which was 4. But since before creating a new way to reach to this 4, you have broken the existing one, so the 4 is lost. So this is incorrect. So that's why the correct way, update new dot next with current dot next. We are temporarily storing this current dot next so that it is not get lost, and then update the next of the current. Is it clear? So insertion should always be handled carefully, because like the only issue with these operations are you should not end up in a situation in which the link is broken or the head is lost. That's it. If you take care of these two things in either insertion or deletion, always ensure the code in such a way that the link should not get broken. Once the link is broken, you can't traverse or you can't reach to the subsequent elements which were earlier present or connected to the list. Alright? Okay. So now time complexity. What will be the time complexity of insertion after a specific key? N, right? The worst case scenario would be I am passing a key of the last node. I am passing the key of the last node. What if key was 4? I need to insert X after 4. So time complexity, worst case time complexity will be big O of N. You need to reach to the last node in order to add the newly created node after that. Alright? Okay, so that's all about insertion in a singly linked list. Now let's talk about deletion. Deletion is removing a element X which is already present in the list. Removing a node X. Removing a node with value X from the list. And similar to insertion, it can be done in either 3 ways. The first is I am deleting the head node, which is the first node. Deleting at beginning. This is my node. I have removed the first node and this becomes my head. Or I can delete it at the end. I have this linked list, the last one which is pointing towards null. I want to remove it. That's it. Head remains the same. And finally, third scenario, I need to delete X and currently X is present after key, after a given key. So it's 1, 2, 3. So remove after 3. Remove the node, say after 2. Okay. In this case, this 3 will be removed, and like it can be anything. Since it's the last one, let me add one more node, 4 pointing towards null. Yeah, so whatever node is present after 2 will just remove. Okay, so the newly created linked list after the deletion would be 1 pointing towards 2 and 2 pointing towards 4. There is no node 3 after the deletion. Alright, this is what deletion is. So let's see how to perform deletion, or let's see how to update these links in such a way that the list remains intact. Okay, the first is delete the head, delete the first node. So the corner condition, check for underflows. What if the list is empty? What if the head is null? Just return. You can't delete anything from an empty list. Second, for instance, there are elements present in the list. You have this one, then 2, then 3, that's it. Correct? So I need to perform an operation in which this is my head. After deletion, delete head. The new list should be like this: 2, 3, null, and this should be my new head. Right? This is what deleting the first element is. Whatever the head is, delete it, and the remaining, return the remaining list. Okay. So let's take a temporary pointer pointing towards head. Temp is head. Then head, update the head to head dot next. Head is pointing towards 1. So this line number 4, the operation that we have done at line number 4, what it will do? It will just increment the head by in such a way that now the head is pointing towards head dot next. Head is pointing towards the next element. It will update the head. This becomes my new head. Okay, this becomes my new head, node 2. And then I have freed temp. Freed was initialized with head. So this was my temp. Initialize temp with head such that even after you update the head, you always have a pointer for the node that you have to delete. Then free that out, free it from memory, and return your new head. Correct? Why it is important to first store the value of the head into a temporary pointer, because you want to try to update head in such a way that head should get updated and now point to the immediate next node. Okay, and once you update your head, there is no way you can go from n2 to n1. Once you reach to n2, there is no way you can go to n1 again. So to ensure that, we maintain a temporary pointer before updating the head, such that I can anytime free that object which is present at location temp. Right? So this is my deletion. Since it's like, what will be the time complexity? Constant, right? It will be a constant time operation. Why? Because we are just updating one pointer and freeing the memory of the previous head. Right? Alright. The next operation, deleting the last node. What if I want to delete the last node? For instance, what if I want to delete the last node? Correct? Deleting the last node. if my list looks like this, 4 nodes, 1 2 3 4, the last is the fourth one. After deletion, the list should look like this: 1, then 2, then 3, and then null. That's it. Head remains the same. Head remains the same. Right? Okay. So again, underflow condition. If the initial head is null, just return. You can't delete anything from an empty list. If head dot next is null. If the second scenario is, what if you only have a single node in the linked list? In that case, what if the list is like this: 1 null, and this is your head, right? So line number 3 4 5 is to ensure that if there is only single node, then just free that head and return null, right? Why? Because we want to delete the last one, and last and first is same in this case. This is also a corner case, better to handle it, but once understood, can be ignored. Okay, the actual implementation starts from line number 6, which is take a temporary pointer called current. Take a temporary pointer called current, right? Initialize it with head. Initialize it with head. Okay. Now the important point which distinguishes the deletion operation with insertion is whenever I want to insert an element after a specific key, I reach to that node and then perform that operation. But for deletion, if I want to delete a specific element, I need to reach I want to reach a node which is pointing to a node before that element. Why? Let's understand this. This is node X and this is node Y. Okay, I want to delete node Y. I want to delete node Y, and deleting node Y, what does it means? My X should point to null and this Y should get freed. This Y should get freed and X should point to null or anything which is present after that. Don't call it null, let's call it Z. After deletion, X should point to Z, right, and so on. It can be anything. Okay. So now what if after traversing, I am at my current pointer is at the node which I want to delete. There are two scenarios. Either you stop at the node that you want to delete, or you stop at the node before you want to delete. Only two scenarios. Okay. So what if I stop exactly at the node that I want to delete? Okay. The problem here is, if you stop at the node that you want to delete, there is no way to go to the previous node. Why? Because you want to update, you want to remove this link and to update it to the next of the node that you want to delete. If you stop exactly at the node that you want to delete, you can't update the next node of the previous object. Is that clear? Why? Because the lists are linked in a sequential manner. If you reach to Y, you can't go back to X. From Y, you can reach to Z. Therefore, in deletion, we always stop a node before the node that we want to delete. That's why there is current dot next not equal to null. Is that clear? In deletion, we will always stop at the node before we want to delete. Why? Because the traversal is in one direction. You can't go back from Y to X in order to update the next pointer of X. You can only go forward from Y to Z. Okay, so there is no way to update the next of X if you stop at the node that you want to delete. Cool. So let me remove it. Or Okay, so line number 7 is the while condition that I just now explained. I need to stop at x in order to delete y. I can't afford to stop at y if I want to delete y, because x can't be updated in that case. That's it. While current.next is not equal to null. Let's come again in this example. I want to delete the last element, right? So yeah, initially my current is this, and I am checking current.next. Current.next will be 2 and current.next will be 3. In this case, it is not null. So just update the current. I will update the current. I will update my current pointer. Again, the same condition, next.next is not equal to null. Current.next is 4. So it is not null. I can update it one more time. Correct? Again, same condition, current.next. In this case, it is null. In this case, it is null. Why? Because current.next is pointing towards 4. Whose next is pointing towards null? So we stop exactly at this point. Why? Because I need to delete the next element. So if I want to delete a specific element, I have to stop a node which is just before the node I want to delete. Otherwise, there is no way to update this pointer. That's why there are 2 next in this while loop, right? So now what will be the next operation? I will free current.next. Currently, my current is pointing to 3, which is a node before the node I want to delete. So current.next will be the node which I want to delete. So I will just free it out. Line number 9 will just free the memory of 4. It will just free it out. Okay. And then my current.next is equal to null. Current.next, this is current, and current.next is equal to null. Earlier it was pointing towards the node that we wanted to delete, which is 4. So we freed it out and updated the pointer of the current to null. Okay, this is, and return head remains the same. This is how you will delete. I am repeating again. In insertion, if you want to insert an element after a specific key, you go to that key and then add the element after that key. But in deletion, if you want to delete an element after a specific key, in that case you need to stop at a node which is just before the node that you want to delete. Why? Because if you stop exactly at the node you want to delete, there is no way going back or to the node which is just immediately before that node. So x.z is not possible. Linking x to z is not possible if you are at y, but x to z is possible if you are at x. How? Let me once again explain it to you. Okay, you have this situation, x then y then z, and current is pointing towards y. So x dot next should point to z. In this case, what is the meaning of deletion? Deletion is initially x is pointing to y. Now after deletion I want x should point to z. But this operation is not possible if the current is y. If you stop at y, x dot next, you can't update it to z. But other way around, if you exactly stop at x, this is x, this is y, and this is z, and this is your current. Okay, at this point you can update it like this. You can update current dot next. Current dot next is y, again dot next. No, current dot next is this pointer. Current dot next is equal to current dot next dot next. Current is x, current dot next, initially at this point it is pointing to y. So this current dot next is z. This is z, and this is the pointer of the node which is just before the node that I want to delete. So I am updating this x to z. I am pointing this x to z and I have removed this link. Now at this point I can easily free it out. So you can first free it and then update as well. It is totally fine. Okay. First you have to free it, otherwise if you just update, then there is no way to reach to y. If you remove this link and you can't free it out. So first free it out and then update the link. Or you can also take a temporary pointer. You can take a temporary node. You can do it in this way also. Temp is your current.next. So in this case it is y. Temp becomes y. And just update current.next to current.next.next and then free temp. It will also work. Okay. Alright. Now the time complexity. Deleting at the last. Time complexity will be big O of n. Time complexity will be big O of n. Why? Because you want to delete the last element. In order to delete the last element, you need to update the pointer to reach to the second last element. So there are n-1 traversal. So complexity remains the same. Next one, deleting by key. So now it's you need to understand it carefully. The idea remains the same. If you want to delete a specific key, you have to stop exactly before that key to update the pointers correctly, right? So I want to delete this key. I want to delete. It is not after deleting a specific key. It is deleting. Let's have an example 1, then you have 2, then you have 3, 4, null. Now you want to delete 3. You call this delete key is 3. I want to get rid of this node. Okay, so the new node would be 1 pointing to 2, then 4, null. That's it. Okay. Alright, so let's corner condition. Head the data is the key. That node that I want to delete is head itself. So you can handle it out. The regular scenario would be from line number 6. You take a current, point it to head. This is your head. You take current, point it to head. Idea remains the same. If I want to delete 3, I have to stop at 2 in order to update the pointer which is currently pointing to 3 to 4 and then get rid of this 3. Otherwise I can't update the next pointer of 2 to the 3.next. Okay. Alright. So current.next should not equal to null. This check is for the end. I should not reach the key. What if the key is not present? What if the delete function is called with, say, delete 5? 5 is not present. So this check will ensure the key is present or not. Key not present. But say it's present. In this case, key is 3, it is present. So current.next.data should not equal to key. Current.next. So the value of current's next should not equal to key. If it is equal to key, then stop. If it is not, then update the current. In this case, current's next data, which is 2, is not equal to 3. So I will update current to 2. Correct? Now, current.next.data. Current's next data is 3. So I will stop update. This will stop. So I have ensured to stop exactly a node before the node I want to delete. That's it. Okay. So now line number 9. If current.next is equal to null. Now we are just checking whether it is the second last node or not, whether we are deleting the last one or not. So not found, you can ignore it. If so, this is what I mentioned in the previous one. We are taking a temporary pointer, temp to current.next. Yeah, so in this case, temp will be the node that we want to delete, right? Because we have already stopped at the node which is just before the node that we want to delete. Then just update temp to current.next. So temp becomes 3, right? And then current.next is equal to current.next.next. We remove this link and bypassed 3, so that 2 is now pointing to 4, and we'll just free this temp out. We'll just free it out. Free temp and return the head. This will successfully delete the key, which is 3 in this case, right? So that's how you will be deleting a specific key in a linked list. You have to stop at a node just before that, and you can just update the link, ensuring that you also maintain a link to the node that you want to delete, so that you can free it from memory, and that's it. Return the head. Okay. All right. Okay, so it's one more type of problem in which you have been asked to reverse a linked list. So let's see how we can reverse a linked list. So there are two approaches that we can follow in order to first, let's discuss what exactly is the meaning of reversing a linked list. Let's assume you have a list starting from 1, then 2, 3, 4 and null. That's it. Let's suppose you have a linked list of 4 nodes. Then this will be your head, right? So in case of a singly linked list, the reversal will simply reverse all the links. So we are starting from 1, then 2, then 3, then 4. Finally 4 is pointing to null. The reversed order would be will start with 4, then 3, 2, 1. 1 will point to null, and this will be your new head. So the reversal of this linked list would be a list which looks like this, and you will just return the head pointer, which is pointing towards the last node of the original list before we reversed it. Okay, so this is what reversal is. Each and every link is reversed. Each and every link is reversed. This is removed, and this became null. Right? So let's see how we can reverse a linked list. So there are two methods. The first is iterative approach. The second is recursive approach. So either way you can implement the reversal of a linked list. So let's see the iterative approach first. So we are not calling any function. We are just call a loop, and iteratively we try to reverse all the links until the last link is reversed. Okay. Alright, so for this iterative approach, we need to maintain 3 pointers at a time. Let's call them previous, current and next. There are 3 pointers that we will be maintaining in order to reverse the linked list in iterative approach. The first is previous. Initially we have initialized the previous with null. So initially previous is null. So this is previous, and its value initially is null. Right? Previous is null. Then current is your node. What is the node? Node is basically the head. We are calling this reverse iterative with head. So node will be your head. So this will be your current. Right? Initially previous will be null and current would be your head, which is the starting node of your linked list. Then you start with a while loop. We'll check while current is not equal to null. We will iterate over this list until this current points to the next of the last element, which is the last node, which is null. Okay, until current is not null, we keep on iterating. First step, you take one more temporary pointer called next, and it will always point towards the next of the node which is next to the current. So in this case, the node 2 will be next. This will be your next, right? So at this point, previous is null, current is your head, and next is the node which is immediately next to the current. Okay. So now we'll one by one reverse all the nodes. Starting with these 3 steps, we'll reverse each and every node one by one. Okay. Let's see how. First step, current dot next is previous. What we are doing, we are removing this link current dot next. Current dot next is pointed towards previous, which is null. So what we have done, initially node number 1 was pointing towards node 2. So we have removed this link. Now node 1 is pointing towards null. This is what the final step. In your reverse linked list, node 1 will point to null, right? So this line number 5 will update the next pointer to point to the previous one. Initially the previous one was null. Okay. Next, previous becomes your current. After you successfully reverse the link, your new previous, this will no longer, this will be, no, we are not removing current, we are just updating the previous. We are just updating, previous becomes current. So previous is now no longer null, previous is now this. Now at this point, after line number 6, both previous and current are pointing towards node 1. Okay, then your current becomes your next. Your current becomes your next. Your current becomes next. Right? So once the first iteration is over, you have incremented the previous by 1. Earlier the previous was pointing towards null. Now the previous is pointing towards node 1 after first iteration. Your current is pointing towards second node. And the next remains the same. Why? Because we are updating the next when we are entering inside the loop. Line number 4 is responsible to update the next. Okay. So iteratively, one by one, we will reverse all these links. Okay. So what will be the next step? Now we'll check for current is equal to null or not. In this case, current is pointing towards 2. So it's not null. So we'll enter into the while loop. Line number 4 will update this next. This will be your next. Right? This will be your next. Now what will be the next step? Current dot next will become previous. Current dot next will become previous. Current dot next will become previous. We have removed this link and now the current's next is pointing towards 1. We have added this link. Right? So in each iteration we will keep on updating these, we will keep on reversing these links one by one. Next step, update the previous. Update the previous, then update current. That's it. And you keep on doing it until current becomes null. So the next iteration, when we enter the loop for the third time, the third iteration, next will be this. This pointer will be removed. Your current dot next, which is this link, is removed and now it will point to 2. Now 3 will point to 2. Okay. Earlier 3 was pointing towards 4. We have reversed 3 dot next. Current dot next now is previous. Then you will update previous. Then you will update current. Right. At this point, current is not equal to null. So there will be one more iteration. Why? Because the final link is still there. 4 won't point to null. 4 will in fact point to 3. Okay. So at this point, your next is removed. Next becomes current dot next. So at this point, next becomes null. Next becomes null. Next is pointing towards null. Current dot next, which was earlier null, now we will remove this link. It will point to 3. It will point to previous and will update the previous. Then we'll update the current. At this point, after the fourth iteration, current is null. So this becomes false. Current is null. Whenever the current is null, it is the iteration is over and you have successfully reversed all the links. And you simply return the previous. Why? Because previous will point. In this case, previous is pointing to the last node, right? So we will return previous and then finally we'll update the head with this previous. After the last iteration, this previous becomes my new head. This becomes my new head. That's why whatever is getting returned from this function, we are assigning it to head. This becomes my new head. This becomes new head. Okay. So all the links are reversed. 4 is my new head, 4 is pointing to 3, 3 is pointing to 2, 2 is pointing to 1, and 1 is pointing to null. That's it. So this is reversed. Alright. So this is how the iterative approach of reversing a linked list works. Alright. And what is the complexity? What will the complexity of this recursive approach of like reversing the list? Not recursive, the iterative approach of reversing the list. Big O of n, right? Because you are iterating until current becomes null. Initially current is your head until the current becomes null. So it will be big O of n, right? Okay. Now there is one more approach, which is recursive approach. So I want you to understand this as a homework assignment, right? So this is also not that difficult, and similar problem we have discussed in queues, in which there was a recursive function that is reversing the queue, reversing the elements of the queue. If you remember, we had done I is equal to delete, then call that function again, and finally insert q comma I. We have done this problem in practice, right? So this was reversing the elements in the queue. So similar approach will be used in order to recursively reverse the linked list. Here's the code. So you can go through the code, you can have the basic understanding. You already know how recursion works, how stack works. So you will be able to figure it out. And even if you didn't understood, then you can easily you can ask in the class. Okay, but try it out. It is also an interesting approach. So now let's see few of the practice problems. This was asked in CS04 2004. The problem says let P be a singly linked list. A singly linked list is given to you. They're calling it P, and let Q be the pointer to an intermediate node X in the list. Any specific node X in between the list, let's call it Q. So P is a singly linked list and Q is any intermediate node. What is the worst case time complexity of the best known algorithm to delete the node X from the list? What is the worst case time complexity of the best known algorithm to delete the node X from the list? So you have been asked the worst case time complexity of the best algorithm which you can use to delete the element, and it is given that the linked list is a singly linked list. It is given that P is a singly linked list. And there is some intermediate node X. Let's assume this is X. Okay, so this becomes Q, right? The node is Q, with basically a pointer to this node, pointer to X is Q. Okay, so you need to tell the worst case time complexity of the best known algorithm. So is there something called best known algorithms when it comes to deleting a specific node in a linked list, in a single linked list? No, right? All algorithms are same, or there is only one algorithm. Why? Because it's a singly linked list. In order to delete any specific node, you need to iterate and reach to a node which is immediately before that node in order to delete it, right? So there is no concept of best known algorithm to delete a specific node. Okay, so basically the question boils down to you need to give the worst case time complexity in order to delete a specific node. That's it. Okay, so what it will be, we have discussed this in class. So what if Q is the last element? What if Q is the last element and the linked list ends here? This will be the worst case. This will be the worst case. You need to iterate one by one over each nodes in order to reach a node which is just immediately before it. Which is, say, let's call it X minus 1 or Q dash. You need to reach this Q dash in order to remove this link, free Q, right? Then only it will get deleted. So you need to perform n minus 1 iterations in order to reach. This is the worst case. What will the best case? But best case will be Q is the first node. You directly delete it. Okay, so it will be big O of n. So it's simply asking you what will the worst case time complexity of delete any specific node in a singly linked list. All right. Okay. One more problem. It was asked in CS 2018. The problem says a queue is implemented using a non-circular singly linked list. So they can simply write singly linked list. A singly linked list is given, okay? And you need to implement a queue using a singly linked list. The queue has a head pointer, alright, and a tail pointer. So 2 pointers are given in the linked list, head and tail. Head is pointing towards the first node of the list, tail is pointing towards the last node of the list. Okay, as given in the figure. Let n denotes the number of nodes in the queue. Okay, let nq be implemented by inserting a new node at the head, and dq be implemented by deletion of a node from the tail. Okay, so now in queue we have two operations, nq and dq, and you need to implement a queue using a linked list, and in that linked list you have given 2 pointers, head and tail. Head is pointing towards the first node, which is the regular scenario if a linked list is given, and tail is pointing towards the last node. You need to implement nq and dq. Nq, what will it do? Nq, say x, it will add a node x at the start. Okay, this is what nq is. We need to add a node at the head, and dq will remove a node from a tail. What will dq do? dq will simply remove the node, and like tail will be then node which is before that node, the second last node of the list. Okay, the question says which one of the following is the time complexity of the most time efficient implementation of nqs and dqs respectively for this data structure. All right, so let's simplify the nq operation first. Let's simplify nqx. What it says, nq is adding a node at start, adding a node at start, okay, which is on the head pointer. So we have seen it. Inserting a node at the beginning of a linked list is what nq operation is, and if you have given this head, you can do this operation in constant time complexity, big O of 1. Yes or no? This is simply inserting a node to the beginning of a linked list. This is what nq is. Every nq will add a node at the start. That's it. So this is big O of 1. No doubt about it. So the answer will be either A or B, right? nq will be always a constant time operation. We need to just point the newly created node towards head and just update the head to point to x. That's it, right? Okay, now the next operation, dq. dq, remove the last element. Remove the last node, not element. All right, and at the same time, so a pointer is given to us in a linked list. Say 1, 2, 3, null. Now a pointer is given to you, which is tail. A tail pointer is given to you. Now tell me one thing. If I want to delete a specific node and a pointer to that node is given to me, can I delete it? No, right? Why? Because in order to delete this tail, I need to reach to a node which is immediately before tail, which is this node, in order to delete. Otherwise, how will I update this link? I can't update if I am at the node which I want to delete. This we have discussed in deleting a specific key. In order to delete a specific key, I need to stop immediately before that node to delete that key, right? So if tail pointer is given, this is of no use for me. I can't use this tail pointer to delete the node which is pointing towards the specific node. Okay, so in order to delete, I need to iterate all over starting from head in order to stop at tail -1, a node which is immediately before the last node. So this tail is of no use. We can't use it. or irrelevant. Okay, so therefore DQ operation, remove the last node. It will have two operations, removing the last node and second updating the tail. In order to remove it, it will take big O of n. This is simply deleting the last node of a linked list. This is what DQ is. Okay, so it will take big O of n, right? So correct answer would be B, not A. So if in the problem the tail was pointing towards the second last node, the tail is always pointing towards the second last node, and DQ operation was defined as removing the last element, in that case A would be the right answer, but not in this case. Why? Because tail is pointing to the node that we want to delete. So you can't delete a node that you have, like, for which you already have the pointer. You need a pointer which is pointing to the node that we want to delete. That's it. Alright, so therefore it will be a big O of n operation. Okay. Alright, one more problem. What is the worst case complexity of inserting n elements into an empty list? So initially an empty list is given to you, there is no node, you want to insert n elements. If the linked list needs to be maintained in sorted order. Okay, so this is the catch. You need, every insert should always ensure that the list after insertion remains sorted. Okay, so you have to give worst case time complexity. Worst case time complexity is being asked. Okay, so let's discuss both worst case and the best case scenario if you want to insert elements in a linked list so that the order is maintained, order is sorted. And let's assume we are like talking about increasing order. Okay, so there can be two scenarios. Either you are inserting 1, 2, 3, 4 and 5. Okay, case 1, or it can be case 2. You are inserting 5, then 4, 3, 2, 1. Let's assume I want to insert 5 elements, 1, 2, 3, 4, 5. There can be two opposite scenarios. Either you insert in increasing order or you insert in decreasing order, out of which one will be a best case, the second will be the worst case when it comes to inserting it in a linked list which is initially empty and the order is maintained. Okay, let's see how. First discussed case 1. I want to insert 1. Initially the list is empty. I will just insert 1 and it will point to null. That's it, right? Next I want to insert 2. In order to be list in sorted order, 2 should be towards the right hand side of 1, right? So 2 should be like this. Okay, then I need to add 3. 3 should be towards the right hand side of 2, which is towards the end. In this case, if you see the pattern, I am always inserting the element towards the end in order to maintain the sorted order. It will be 1, then it will be 2, then 3, right? So how many insertions are required for this operation? If I want to add 2, add 1, add 2, then add 3. Okay, for adding 2, I need to perform one operation. Why? Because I need to insert it after the first element. So one operation, the loop will be running one time. In this case, I need to run the loop 2 times. Add 4. It will be like this towards the end. Why? Sorted order is maintained. The loop ran 3 times. This is for like analyzing the complexity. And finally add 4. Add 5, not 4. Okay, so the iteration will run 4 times. If you sum it over, it will be 1 plus 2 plus 3 till n minus 1 if I want to insert n elements. Okay, So the summation will be n minus 1 n minus 2 by 2. It narrows down to big O of n square time complexity. Big O of n square time complexity, right? For this case. Now the next case, what if I insert the elements in this order? 5, 4, 3, 2, 1. Case 2. Okay, I add 5. Initially I add 5. No problem. Just add one element, add one node. Then I have added 4. So what will be the position of 4? It will be at the beginning, right? Because 4 is less than 5. So the order in which the sorted order I need to maintain, it should be like this, correct? Now add 3. What will be the correct position of 3 so that the sorted order is maintained? Initial, right? I just have to insert 3 on the head. Can you see the pattern? Can you see the pattern? For inserting 4, I need just one operation, a constant time operation. This is also a constant time operation. Add, not 4, add 2. 2 will be again at the head. Inserting an element at the head is always a constant time operation. Inserting an element towards the end is not a constant, is a big O of n based on number of elements present in the list initially. 3, 4 and 5. 5 is pointing to null. Again constant time operation. Finally you add 2, not 2, add 1. 2, 3, then it will point to 4 and finally it will point to 5, which is the last node pointing to null. This is also a constant time operation. Sum it overall, it will become, the summation will be n minus 1. The complexity would be big O of n. Okay, so out of these two scenarios which are extremely opposite, one is the best case, the second is the worst case. So case number 1 is the worst case. Case 2 is the best case. Okay, so in the problem we need to tell what is the worst case time complexity. Answer is A, big O of n square. If they've asked what is the best case time complexity, the answer would be B, big O of n. Alright, so that's how you simplify these sort of problems. Alright, so let's discuss how the linked lists are implemented in Python. So we will be starting with singly linked list, the most basic one, in which the structure of a node will look like this. It will be having two parts. First is the data, also known as the key or the value that the specific node is holding. Second is next. So if we are talking about C or C++ programming language, this next used to be a pointer. This is a pointer or reference which stores the reference or the address of the immediate next node, right? So in general, a list looks like this: a series of nodes where the first node has a key and the address of the immediate next node. Then the second node has its key and the address of its immediate next node, and so on until the last one. It is a chain of objects, and the address which we store in the last node is null, or nothing is there, or the chain ends at this point over this node, right? And the first node is always considered as the head node. The nomenclature is like this: the first node is the head node, and usually we maintain the address of this node, because if we have the address of the head node, all the subsequent links can be traversed using this address, right? or the second scenario, if we lose this head, in that case few of the links will be lost or there will be a data loss, right? Okay, but in Python, when it comes to Python, there is no concept of pointers over here, right? So the nodes look like this. So let's assume you have three nodes. One, next is two, its next is three, and null, right? So in Python, how will we will be storing these nodes? There will be two components, right? There will be first the data, which is the key, and the next value. But in this case, the next will not be a pointer. The nodes in Python will look like this. We will be having a node which has data and next, but next is not a pointer. Next is in fact, let's assume, the representation of what exactly a node, a linked list with three nodes will look like in Python. The first node will be having data value 1 and there will be next pointer. This is data and this is next of the first node, right? And it is head as well. You will call it head. The next will not be a pointer in this case. The next will be stored. There will be another node which we will be storing in the next, which again will be having two parts, data and its next. Data will be 3, and then in this next, the next of the inside node which is having key as 2 or data as 2, there will be another node with value 3, and the next will be null here. Or in Python we do not have null. Rather than null, the corresponding null is none in Python, right? So it won't be null, it will be none. So this is how a chain of 3 singly nodes will look like in Python, right? Okay, so let's start with defining a class of node having two parts, having two counterparts, data and next. Then we'll create an object which is the head pointer of this linked list, and then chain up with the subsequent nodes 2, 3, and then we'll perform certain operations that we have in linked list. Okay. All right. So class in Python is defined like this. Let's name it node, and in node we'll be defining a constructor. We're defining a constructor, and constructors are defined like this: double underscore init double underscore, and init stands for initialize or initialization, and constructor is basically a function which always triggers whenever you instantiate a new object of a class, right? And whatever function you define in a class, the first parameter will always be self. Self stands for the reference to the current object, right, of which you are either calling this function or instantiating an object. Then you will pass some data. Whenever we instantiate or initialize a new node of the linked list, we have to pass the key, which will be the value of that node, correct? Whenever a new node is created, it will be having a value or data. So this data is the value of the specific node which we are creating or defining, right? And then there will be the next component which will be null at the time of initialization. Okay, so it will be data, and the data objects are referred by self in the class, right? So it will be self dot data, which is the data that we are getting as a parameter in the constructor, and then there will be the reference of the next node, and initially it will be null, right? So that's it. So like a class is already defined. Class has two components: data, which is the value of the key, and the next. In this next, we will be storing the immediate next node. Let's see it how. So first of all, let's define a head with value as 1, right? What it will do, it will create a head node with data as 1 and next as none, right? So initially it will create a head node with data as 1. What it will do, it will create a node like this in which data is 1 and this is none, and we have named it as head. This will be our head, right? Okay. Now once the head is created, let's create few more nodes and chain up with the head, right? Like we can refer these immediate nodes with some other variables, but we can also do it like this: head dot next. This is the next part of the head. Let's create one more node, add this next with value 2. So it depends on how we are creating or chaining up the nodes in the list. 3. Let's create one more. You can also have a loop. I am like defining in a brute force manner. We can also have a loop, take input of number of nodes that we want and keep on adding them. Right. So what it will do, what we have done here is, first of all, at this point, we have created a head node with value as 1, right? And the next is as null. Why? Because at the time of creating a new node, the next is always assigned as none, right? So at this point, it will be none. Then we have added one more node. And what we have done, head dot next is my new node's address or the reference. We won't be calling reference in Python. It is better that we are in fact assigning the entire node to the next here, right? But vaguely, we since we all are we all have learned linked list to be in the blocks of data which are chained up together. So let's keep that only. The next will be having 2. Its next will be having 3 value, and finally its next will be having another node with value 4, and this will be none. The next of the last node will be none. But internally, what we are doing here, we have created one node, its value is 1, created one more node, its value is 2. Inside its next, there is one more node with value 3, and finally one more node with value 4. And finally, this is none, right? Okay. So now let's traverse and try to print, starting with this head. This is our head. So starting with this head, can we traverse this list? So it should give us 1, 2, 3 and 4. That's it, right? If we are starting with head and try to read the keys, try to read the data sequentially. So let's see. Okay. So traversing the linked list. Let's define a function. Or let's call it print linked list. Will pass the head, and what will be the idea behind printing the sequentially linked nodes? We will keep on, there will be a loop, right? There will be a loop, and we will keep on continuing the search until we encounter this, until the list ends, right? Okay, starting with head. So head is already passed, which is the first node of the list, right? Okay, so head while head print head dot data, then print arrow, so that it gives us essence that they are chained up together, and then updating the head by its next. Let's call it current. Right, and let's call this function now println, and we will pass this head as the argument of this print function. Cool. It is giving us data like this. There is 1 and then arrow, again 2 arrow, 3 arrow, and finally 4. So it has stopped exactly when at node 4. After node 4, when the current is updated to its next, the last node's next is null, and it's exactly the point at which this while is terminated, right? Okay. Cool. So this is how we can create a node and then chain it up together or link it together in a single linked list in Python, right? So this is our search operation, or like a not search. It is exactly it is the print operation or the traversal of the list. So now let's see how we can insert a new node after a given key in the list. Okay, so we'll use the existing list, which is we have 4 nodes, 1, 2, 3, and 4. So inserting a node after a key. Okay, let's define an insert function. Insert in linked list will pass the pointer to the head, then a key after which we want to insert, and the value of the new node, the data of the new node. Okay, and the idea will be, how will we do it? So we already have a link. We have a list like this. It's 1, its next is 2, then we have another node 3, and finally 4, and its next is none. So we want to insert, let's assume the key is 3. I want to insert a new node with value x as 5 after 3. So I have to create a new node, assign the value x to it or 5 to it, and then update the links of the existing chain in such a way that 3's next should point to x and x next should point to 4, and this should be removed. The link from 3 to 4 should be removed, and a new node should be added in between 3 and 4. Okay, so as we discussed in the class, in order to add a new node after a specific key, first I need to reach to that node. So starting with head, first we will be searching for the node with the value key, which is this. Let's call it current, and then the updating the pointers is not a big deal. Okay, so let's see how we'll be doing it. Okay, so let me take a temporary pointer called current. Initially the value is head, and a while loop, while current, and we are searching for the key, right? We want to exactly stop at the node whose value is equal to key. So I will check whether my current's data is equal to key or not. If it is key, in that case it's like we have successfully find the key and the current is pointing to the key, after which I need to insert a new node with value x. So this is the point where I will declare or initialize the new node. Let's call it new node, whose value will be x, right? And then once I have initialized a new node, let's say this is 3 and its next is 4, and this is my new node with value as x. So what I need to do, I need to update new nodes x to point to 4. I need to remove this link and update the current key's next node, next value to x, such that it should create a new link like this. After 3 it will be new node, and after new node it will be 4, and the list continues, right? Okay, so it will be my new nodes next will be currents next, which is 4 in the reference example, and then currents next will be the new node. Okay, so at this point we have successfully linked my currents next with the new node and new nodes next with the currents next. Okay, and just like a return head, that's it. But this is not the end. After, if we have to increment this current such that in each iteration, in the next iteration, current should always point to the immediate next if we haven't found the key yet. And at the end, what if the key is not present? So it will be like, if the key is present, this return will execute and terminate this function, right? But if we are out of this while loop, that means the key is not present. So just print the warning that the key is not present. Okay, the key is not present, and return the head. All right, so let's call it. Before calling, let's print the linked list with the head. This will give us the existing links. Initially it is 1, 2, 3 and 4. Okay, let me print a message as well. Before adding, let's assume we are adding 5. Before adding 5, print the list, then head will be insert the link into the linked list starting with head, then key would be after 3 I need to insert, and the value should be 5. Okay, and since we are returning the head, so it should always be initialized with the current head, like it should always be replaced with the current head. Then let's print again. After inserting 5, and finally we'll print the list again. Okay, let's see. Okay, so before inserting 5, the list was 1, 2, 3 and 4, and after inserting 5, we can see that 5 has successfully inserted between 3 and 4. Okay, so now let's try to insert after a key which is not present in the list. In that case, this should print. So what if I want to insert a key, let's say 10, insert 20 after 10. In this case, 10 is not present in the list. After insert, this is my new list, 1, 2, 3, 5 and 4, in which 10 is not present. So it is giving the error 10 is not present. Okay, and the list remains the same, 1, 2, 3, 4 and 5. Correct? This is how you will be adding a link after a specific key. Okay, and now you can tweak it to insert a new node at the beginning and at the end of the list. You can take it as homework. Inserting a node at beginning and at the end. Okay, now let's see how we can delete a node. Deleting a key, right? So the function will be delete. In this linked list, we'll start with head and a key. A key would be sufficient. Why? Because I am trying to delete a key. So this is my final, like at this point, this is the linked list 1, 2, 3, 5 and 4. Let's say I want to delete the newly added key, which is 5. Okay, so as like we discussed in the class, if we are trying to delete a node in case of a single linked list, if the list is like this, which is in our case 1, 2, 3, 5 and 4, if this is the list and I am trying to delete a node with key as 5, I want to delete this. So in order to delete this, I want to stop exactly at the node which is just before the key that I want to delete. So I will stop at 3. So I will stop my current at 3, which is before 5, not at 5. If we have the reference of the node that we want to delete, in that case you can't update this previous point, the next node of the next pointer of the previous node. Why? Because there is no link in backward direction such that you reach to the previous node. This is not possible. So we have to stop exactly at a node prior to the node which is having the key I want to delete. Okay. All right. So if it was like, if I want to stop exactly at the key, this will be the case, right? Let me copy it and we'll tweak it such that I am stopping a node before, right? So this remains the same while current, and let's tweak it currents next not equal to key. Currents next is not equal to key. Okay, if currents next dot data is not equal to be, keep on updating current, right? So let's print current dot data over here. I'm not trying to update anything. We'll call it with head and key as 5. Okay, so we are getting the pointer. It is returning 3. So after this while loop, we are exactly at the node which is prior to the key that I want to delete. Okay. All right. So now what will be the deletion process? In order to delete, this is my 3, this is my 5, and this is my 4 and none, right? So and I am here current. So I just need to update the next of the current with currents next dot next. I need to remove this link and update its next to the currents next dot next, which is 4, correct? And will free this node, which is currents next should be freed. Okay, so we will do exactly this. So at this point, let me have a temporary pointer or a temporary variable to have the reference of currents next. Okay, then I will update my currents next with temps next, and temps next is currents next dot next, and finally delete temp. Okay. Finally delete temp. This is after delete. Let me print the head again. Okay. Alright, we have successfully deleted a node after a specific key. So after delete, when I print the linked list, it is giving me 1, 2, 3 and 4. That's it. This is how you will be delete. This is how we will be deleting a key. So now you have to add two things. So add a check in the above function or delete linked list function for key not found. So let's call it homework 1 and then write function to delete the head and the last node. Okay, so these two are in homework. So that's how we will be having the operation in a singly linked list in Python.